Hi guys, Mark Heath here, and today we're looking at the solution to day 18 of the advent of code in C# and F# as usual. And today basically the challenge is to implement the game of life algorithm. And if that's not something you're familiar with, basically we start off with the lights in this problem, or cells, being either on or off. Represented off is a dot, on is a hash, and there are rules about every time you go to the next step in the sequence whether they stay on or off, or whether they change. And it depends on what the state of their neighbours is. So you count how many neighbours are on, and depending on how many neighbours are on, that governs what state you'll change to. And although this is fairly well known, I haven't ever personally implemented this myself before. So let's have a look at how I did it in C#. And before we do that, I'll just show you my input. The input is one large 100 by 100 grid of these lights that are going to be turning on and off. And we have to animate it through 100 steps. So here in my C# code, you can see I've done the smaller 6 by 6 test input, which was very useful for kind of working out whether my code was right before I tried it on the 100 by 100 grid. And you'll see that I've made a few little helper functions. I started off by parsing the input, and I parsed it into an array of arrays. I'm not sure that was necessarily the best choice. Probably a 2D array would have been better, but it was an array of ints, with 1 meaning the light's on and 0 meaning the light's off. Then I've got a function to get the value of the light, and the reason we can't just go straight to the array and get x, y is because we might be checking the value of a light that's outside the array, because we're trying to get the values of our neighbours, and if we're looking at the neighbours of something on the edge, then our indexes will go out. Then I've got the get the sum of the neighbours, which basically goes through all 8 neighbours of a particular light at coordinates x, y, and adds up their values. And then get next value. This is the kind of the guts of the algorithm, really. If we've got 3 neighbours, then the light is on. Otherwise, if we've got 2 neighbours and the light is on, then we're on. Otherwise, in all other cases, we're off. And so now we need to do our repetitions, which is 100 repetitions, and calculate the next state. And the next state is basically done by iterating through every value in the array and working out the next value. The one gotcha that you've got to be aware of here is that you can't do it in place, because all of the new values must be calculated before changing any values. So we calculate it to a brand new array, and then we just save it to this state variable, which then means we can run our next repetition. And the answer to the problem was to count how many lights were on, which is easy if your array is full of 1s and 0s. You can just sum up the sum of each row. Part B of the problem was basically the 4 lights in the corner were stuck on, and I did actually create a new LinkPad script for that because it involved hacking the code around a bit. The 2 things you had to change, really, and I was a bit annoyed at changing it in 2 places, but that was the easiest way with my solution, was that in the getLight function, if you were one of the corner lights, then you just hardcode returning 1. But as well as in the getLight function, you also, in the getNextValue function, have to check whether you're one of the lights that's stuck on and return 1 there as well. And if you forgot one of the 2 places, you'd get the wrong answer. So my C# solution certainly could probably do with a bit of improvement. I didn't go to great lengths to refactor this after I'd got the right answer. Let me show you my F# solution. I decided, as I usually do with F#, to try and do a few things a bit differently. One of my goals was to solve both parts of the puzzle in one piece of code, and that means that I'm passing this is stuck on function around all over the place, which again could be cleaned up a little bit. But let's just have a look at how this code is different. Well, actually, the first thing I should say before I talk about that is that I chose to actually leave the input in the state it was in. So I was just going to have an array of strings. And the advantage of doing that is that I could print out my array at any time and more easily check that my algorithm was working. So I just need to read all the lines of the file into an array and we'll work directly on that. And so to check if a light's on, if it's outside the bounds, it's not on. If it's stuck on, then it's on. Otherwise, we check if we've got a hash character in that position. To get the sum of our neighbours, this is probably a slightly nicer way of doing it than the C# version. We have the 8 coordinates to help us calculate a neighbour, map that onto the coordinates we have, and then filter out any lights that are on and count the length. And getNextValue also benefits from pattern matching in F#. We first check if the light is stuck on, and if not, we just use the getNumberSum function to count how many neighbours we've got that are turned on, and if we've got 3, we're on. If we've got 2, then we might be on or off, and if anything else, then we're off. And so here in the animate function, this is really where the magic is happening. We need to create a new array of strings, and we can do that with this kind of F# syntax. We're saying generate an array for each x in the length of our grid. Then we're going to create a new string. The string class has a constructor that takes an array of characters. So here we're making that character array, going through each of the column positions and getting the next value for x and y. And then to count the lights, we need to go through each row, and I'm cheating a little bit here. I'm just replacing any dots with nothing and then seeing how long the string is to find out how many lights are on that row, and then sum all the rows together. And then the final bit, to actually repeatedly apply the same function on itself. I wonder whether there might be actually a nicer way of doing this in F#, but this was the best I could come up with. We have a list of numbers from 1 to the number of repetitions, and then we use seek.fold to repeatedly call the animate function on itself. So we start with the starting state and we just keep passing the next state in 100 times and get the final state. And passing this isStuckOn function around everywhere is quite cumbersome and ugly, but it does mean that when we're actually ready to calculate our answers, we can pass in this function that says no lights are stuck on for part A, and for part B we can pass on this function which just checks if the coordinates of the light we're dealing with are in this list. And this works absolutely fine. It performs very badly, probably because of things like this corners on function is not exactly an optimal way of writing that. But it is another way of tackling the problem. And so that's it for day 18. Hopefully I'll see you tomorrow.